Lesson 2-8, and unfortunately I don't have my usual tripod set up, so I've got a little free camera action going today, and hopefully it'll be steady enough for you to read this. Let's start with our vocabulary. First phrase, similar figures. Figures that have the same shape but may not be exactly the same size. That is notated with so if you want to say that two triangles are similar, you would say triangle ABC is similar to triangle DEF. Next word, congruent angles. Those are angles that have the same measure. For some reason, they don't have that vocabulary word here, and they really should. Congruent angles are angles that have the same exact measure. So two 90-degree angles are congruent. Two 45-degree angles are congruent. And the only other vocabulary word I want you to write down is scale, meaning a measuring tool where the ratio of actual size to a smaller figure size remains the same. We'll get into this with one of the later problems. Your book also includes scale drawing and scale model as vocabulary, but if you know scale, you've got scale drawing and scale model. Let's take a look at page 130. So I'd like you to notice on page 30, this getting ready problem makes use of two similar figures. This sailboat and the sailboat model are the same shapes, but different sizes. Come on down here, take a look at these triangles. This is the main point that they're trying to get at in this beginning. Triangle ABC is similar to triangle FGH. And notice how I named all 3 points in the same order on each triangle. If you look closely, triangle side AB is length 8, whereas the similar side FG is 12. Side AC is 10. The similar side is 15 over here. Side BC is 12. Side GH is 18 over here. The sides on these two triangles are all in proportion to each other. And all of these, this angle, angle A, is the same measure. It's congruent to angle F. Angle B is congruent to angle G. Angle C is congruent to angle H. They go through all this down here where they say A, and they've added an extra squiggle over the equal sign. That means congruent. Angle A is congruent to angle F. I don't know why you can't just say angle A is equal to angle F, but in geometry we always use the word congruent. So go ahead and use it and know that that's what that symbol means. Also, like I was saying earlier, the sides, the ratios of the sides are equal. They've got AB over FG, so matching sides. A, the side on the left in this triangle, the side on the left in that triangle. That ratio is equal to AC over FH, the right side of this triangle, the right side of that triangle, and BC, it's also equal to BC over GH. The bottom on this triangle, the bottom on that triangle. Notice that in this proportion, all the sides in the numerator are from the same triangle. All the sides from the denominator are in this triangle. Okay? So, what good is all this? Let's take a look at problem 1 on page 131. So they did it again. They gave you a multiple choice problem, and I really don't like those, so we're going to ignore the whole multiple choice thing. You've got two triangles here, and you know they're similar because they tell you they're similar. So first triangle is ABC, the second triangle is DEF. Because you know they're similar, you know that angle A is congruent to angle D, Angle B is congruent to angle E. Angle C congruent to angle F. And it's a little hard to see with the glare, but they also give you numbers for the sides. You've got AB is 10, BC is 16, DF is 18, and EF is 12. So we're trying to figure out the length of DE. Well, DE is going to be comparable to AB, which is 10. So all we need is two similar sides that we have the measurements for. So if we compare the ratio of BC to EF, we know that the ratio of AB to DE is going to be the same. And down here, you start by writing the proportion, put in the lengths you know, and then you just solve. Now, this first step is actually pretty important. BC over EF. So we have this triangle over the length of this, the side in this triangle. And then AB over DE. The side in this triangle over the side in that triangle. Notice that the top, the numerators, are both from the triangle on the left. The denominators are both the triangle on the right. And then just substitute in what you know. We happen to know that BC is 16. We're given that. So that goes in that fraction. We happen to know that EF is 12. We know that AB is 10. DE is what we're looking for. So that's how we get that far. Then we all know about the magic of cross multiplying, so just cross multiply. You end up with 16 times DE equals 120. Divide, and you're all set. So your first problem is using these figures. What is the length of AC? Pull your notebooks out, see if you can figure out how to set up the proportion. I'll catch up with you in a second. So for number one, we're trying to find the length that is AC. First step, set up your proportion. I have EF over DF equals BC over AC. Now let's match this up with the triangles that we have. Come scooching up here to the book. See if I can get rid of that shadow. EF over DF. So I have both the lengths from this triangle equals BC over AC. So what I did was I set up one side and the similar side, both numerators. One side and the similar side in denominators, and these come from the same triangle, and these come from the same triangle. As you might be able to tell by the word or here, there's another way you could do this. You could set up EF over BC equals DF over AC. So that would be this side over its similar side equals DF, the bottom, over the similar side. So on this one, I did same triangle as numerators, same triangle as denominators. Now, something kind of cool happens. No matter which way you set this up, put your numbers in. 12 over 18 equals 16 AC on this side, or 12 over 16 equals 18 AC on this side. No matter which way you set it up, once you cross multiply, you end up with 12 times AC equals 16 times 18, which gives you 12 times AC equals 288. So you divide by 12, and AC is equal to 24. Go back and watch that again if it didn't quite make sense to you the first time. When you're ready, we'll go on to problem 2. So a man who's 6 feet tall is standing next to a flagpole. The man's shadow is 3.5 feet. The flagpole shadow is 17.5 feet. What is the height of the flagpole? Figure out your proportion. Come back and check with me. So again, there are two ways you can set this proportion up. This way is, I did one side is for the man, his height on top, and the shadow height on the bottom. This side is for the flagpole. Flagpole height on the top, shadow length on the bottom. See, we've got actual height on the top, shadow length on the bottom, the man on one side, the flagpole on the other. Or you can also go the other way, which would be the actual height of the man and the actual height of the flagpole over the length of the shadow and the other length of the shadow. But notice, on the top, both the numbers for the man, and on the bottom, both the numbers for the flagpole. Either way you set that up, you end up with 6 times 17.5 equals 3.5 F, which gives you something kind of like that. Yeah, see, you remember the step from one of the earlier lessons where you can get rid of the decimal? I'm not a big fan of decimals, so I got rid of them, which gives you 6 times 175 equals 35F. 1050 equals 35F. Divide by 35. The flagpole is 30 feet tall. So some quick work with scale drawings. We put the word scale in the vocabulary. A scale drawing is simply a drawing that uses a scale. You see this all the time in maps, right? Check out down here where it says the scale. 1 inch equals 110 miles. So you can do a whole map of Florida, which is a really huge state if you've ever tried to drive through it, across it, around it. As you may have guessed, given the map distance from Jacksonville to Orlando, you're trying to figure out the actual distance. They set the proportion up. I'll let you look through that on your own if these problems are still a little confusing to you. And got it number 3. I want you to figure out the actual distance from Jacksonville to Gainesville. Using the map scale, it's about 0.6 inches. And what's the scale on that map, which you need for this problem? 1 inch to 110 miles. You go ahead and work on 3A. Then let's see what's in my notebook. So I set this proportion up with the measurements on the map on the top and the actual distances on the bottom. This fraction is the scale on the map. This fraction is the specific amount for the number that we're trying to find. So get that set up, cross multiply, and you end up with the distance is about 66 miles. Letter B, you can kind of see my scribbling over here. They ask you to think about it. They don't actually ask you to solve it. Interestingly enough, though, they give me an answer in the answer key. But what I want from you is the thinking part, not the solving part. If you know how far apart two cities are, and you know that the cities are 2 inches apart on the map, how would you find the scale of the map? Something for you to think about. So last, I'm on page 133, problem 4, and we've moved on from a scale drawing to a scale model. Now, I don't think this is the one at the Franklin in downtown Philadelphia, but boy, I think that railing there looks a lot like the one in the Franklin, and I seem to recall a wall that looks like that artery or vein. But I don't remember the heart looking like that. So anyway, we've got this scale model of the heart that's 14 feet tall. And we know that in a 6 foot tall person, we're trying to figure out how big the heart is, given that this heart is the right size for someone who's 170 feet tall. So by now you know the drill. Set up your proportion. The height of the giant heart over the height of the man's heart equals the height of the giant person over the height of the man. So the top is the giant numbers. The bottom is the actual man's numbers. This fraction is all the heart stuff. This fraction is all the person stuff. Put in the numbers you know, cross multiply, solve from there. So the size of the man's heart would be about 5.9 inches. Got it, number 4. Scale model of a building is 6 inches tall. The scale of the model is 1 inch to 50 feet. How tall is the actual building? Set up your proportion. Meet me back here. As always, there are 2 ways to set this up properly. On this side I have the dimensions from the model on this fraction, 1 inch to 50 feet. On this side I have the 6-inch building, and we're trying to figure out how tall the 6-inch building is. So this fraction is all the building, this fraction is all our scale, the top is the inches on the scale, and the bottom is the actual inches. Or you could set it up this way. You could use the two scale numbers as your numerators and the two building that you're trying to figure out numbers as your denominators. This fraction is all scale. This fraction is all actual numbers. Either way you do it, you end up with 6 times 50 equals h when you cross multiply. And you end up with a 300-foot tall building. The rest of your homework for today is page 134. That's a 7. I always start with the first number and then remember that I need to give you the odds. So page 134, 7 through 17, odd. It's not too big an assignment. Good luck.